what we move from is random variables to stochastic processes. So rather than thinking of random variables and Poisson distributions, we move to Poisson processes. Rather than compound Poisson distributions, we have compound Poisson processes. I'll explain all this. The thing we're most interested in is the surplus, how much money we have in reserve or in the bank, so that's the surplus process. Where then the whole section is what's the probability that the amount of money we have in surplus is negative, so that we actually have we're ruined for a particular portfolio, meaning that the amount of money paid out is more than the amount of money come in. So that's the ruin probabilities. And it turns out that they're very hard to calculate it exactly, so there are a number of methods of approximating them again. So one of them is the adjustment coefficient, which will provide an upper bound for the probability of ruin. So we'll learn a bit about what the adjustment coefficient is, how we use it, and as I will hopefully get onto today, but I might not quite make it, there are two types of ruin probability: probability in finite time and infinite time. Now, infinite time is easier to handle, though still difficult. Finite time is more of interest because you usually run portfolios for a finite amount of time. And I will show some results about the probability of ruin in finite time. The things right, if you flick through the notes, the graphs right at the end were obtained using Monte Carlo methods, so I won't actually explain in great detail how we got those graphs until probably the very last lecture of this course. Because again, simulation methods are quite a good way of working out these things. So, well, I've got meant to cover this in 2 lectures. I don't think I will. So I'm going to use a bit of Monday's lecture to cover this, because I was going to go through the class test and the solutions to the class test as well on Monday. So hopefully in the next 3 lectures, which is what I've got scheduled for this, we'll do this section and I'll give you some feedback on the class test. But let's see how we get on today. So as I've said, in risk models, you're looking at the end of a fixed period of time. So what's the distribution of the number of claims, or the claim sizes at the end of a year, say? In ruin, we're following this through time. So we're going to follow processes through time. So claims are going to come in, money is going to go out from claims. We're also assuming we're going to have some income coming in. So we're now looking at stochastic processes rather than random variables. And I'm not going to do a lot of stochastic process theory, just state some results. So the setup is very similar, but the whole idea is that we're following things in time. So clearly claims now x1, x2, x3, x4 are going to come in. So x1 is the first claim, x2 is the second claim, ... as claims come in. We're still going to make the assumption that they're a bit like a collective risk model, independent, identically distributed claims from some loss distribution that I've decided is the best loss distribution. So it could be a Pareto, it could be a log normal. We're then going to have, rather than saying what's the total number of claims in a year, we're going to have a process NT, which is the number of claims up to time t. So I'll say a little more about this, but in a on future slides, but let's get a pen that works. So NT now is a function of t, and it will count the number of claims. So it'll only take the values 1, 2, 3, ... And what will happen at some point in time, the first claim will come in, then sometime the second claim will come in, the third claim will come in. So that's the number of claims up to time t. And I will immediately say, well, the obvious thing to use for that is a Poisson process. So I'll say a little bit about the Poisson process. The next thing is that, okay, so that's the number of claims. What is the total aggregate claim amount of the time t? So I'm going to have another process, which is going to be called ST. So that's that's the aggregate claims up to time t. So it'll be related to this process, but it won't go 1, 2, 3. It'll probably be on a continuous scale, although it could be discrete if the claim sizes are discrete. So at time 1, it'll jump up by an amount x1. Then at claim 1. At claim 2, it will jump up by an amount, say, the size of claim 2. At claim 3, it will jump up by the amount of claim 3. So mathematically, that's that. So as a function of t, what is the value of s at a point t? Well, it's the sum of the claims up to the number of claims you've had here. So in this area, it's just 1 claim. Here, it's 2 claims, etc. So these are stochastic processes. So both NT is a stochastic process. It's a family of random variables indexed by time. And in fact, they're continuous stochastic processes. They're in continuous time. So they're a function of time. So this is NT, this is ST. This one is called the claims process. This one is called the aggregate. So this is the number of claims, and this is the aggregate claims process. Now, just as a side remark here, really, if you decide to stop at any particular point in time, say here, t equals 1, let's say, then what do we have? Well, we have a collective risk model. So if I was to ask, what is the aggregate, what's the expected number of claims at t equals 1, then I can work that out by saying, well, I'm looking at the first unit of time, and I can use the results that we met in section 2, part 1. So for any fixed particular point in time, we can say, what is the mean of S1? Or say at one point, well, that's the standard theory. It will be the expected number of claims up to time point 1 times the expected claim size. And again, if I wanted the variance, I could look at the formula as well. So if I wanted to stop at any point in this process and say, what's the expected number of claims here, and what's the variability, and what's the coefficient of skewness, and what's the probability that this is greater than a particular amount, I can do that from everything we discussed in section 2, part 1. So first of all, let's think a little bit about the Poisson process that we're going to use to model the number of claims. So a Poisson process is a counting process. So it's a family of random variables that can take the non-negative integers. So, and it's always increasing. So it never goes down. So it's not a process that goes up and down. It just goes up and up. So at any particular point, what we say t, the number of claims at time t is going to be greater than or equal to the number of claims at time s, if s is less than t. Which seems, well, that's what we expect. It's a useful thing. And this can be used in all sorts of things. Most of you have done a stochastic processes course. If not all, or some of you have done a stochastic processes course. I'm not expecting you to be able to prove some of the stochastic processes results, but if you have done a stochastic processes course, some of these results will be familiar to you. So the Poisson process starts, by definition, with the number of claims at time 0 to be 0. It makes certain assumptions. So this is the way you can define a Poisson process. You can make assumptions. You say it starts at 0. The number of claims or number of events in non-overlapping time periods are independent. So the number of claims in week 1 will be independent of the number of claims in week 2 in week 22. So if you make that assumption, then this is starting to define a Poisson process. So it starts at 0, times it. So now you're dividing it up. Then you go on to make further assumptions. If you say, what's the expected number of claims in a tiny interval? So what's the expected number of claims in an interval from, well, maybe because I put t here, to t plus delta t? How many claims do you expect to have in this little amount of time? If you then say, Well, that is approximately going to be, and as t gets small, delta t gets smaller, it tends to this result. It's approximately going to be the rate of claim per unit time times the length of the claim. So that's the probability of one claim in a small event, or event in a small interval, will be the average number of claims per unit time times the length of this small claim. So, of course, if we're getting 10 claims per week and we're going down to seconds, then it's 10 claims times what proportion a second is a week, so a very small amount. We make the assumption that, in some senses, the third one's the next line. We make the assumption that this is so small that it's impossible to have two claims in there. So, well, it's near enough zero probability of having two claims in there, and then the middle one of those three follows, because if you can have one claim with this probability and two or more claims is impossible, then the probability of no claims must be 1 minus the probability of one claim. And the lambda here is called the rate, or intensity of the process. So it's the same, it's related to the rate. It's sometimes called the rate as well. So intensity, which is a new word because it's a process, or rate, which you've met before for a Poisson distribution. And I'm not going to do it, but if you go to a good stochastics process book, you can prove under these statements that I've written on the last slide and here that the number of events in a time interval 0 to t will follow a Poisson distribution with rate, and this is where you've got to remember it will be lambda times t. So this is where people make a slight mistake. Remember now, you've got to say lambda is the number of claims per unit time, and we have to say how many units of time are we interested in, 2 units or a half unit. So the Poisson distribution will say that the number of claims up to, say, s will be s times, will follow a Poisson distribution with rate s lambda, or up to t would be t lambda. Therefore, the probability of no claims will be e to the minus lambda t, and of course, the probability of n claims in this interval, 0 to t, will be this. So that's the Poisson mass function, but of course, the parameter is, this is the average number of claims per unit time times the time interval we're looking at. So we have to remember that. And I'm saying that a number of times because I'll find examples where people forget one or other of these. But think about it. If there is one claim per week, which is lambda, and we're looking at 5 weeks, then the expected number of claims in 5 weeks would be 5. So this is one result that I'm not going to prove, but it's a stochastic processes result. Another important result that you can prove from that, or you can, depends which you start from, that's the thing in mathematics, the probability theory. If you can prove A from B, if A if and only if B, then B if and only if A, but this is the way. If you set this up and then ask yourself, what's the distribution between events? So what's the length of the time between a length? So what is the distribution of these inter-claim events? Then it follows that if the claims are coming from a Poisson process with rate lambda, then the intervals between them will follow an exponential distribution with rate lambda, exponential with rate parameter lambda. Okay? Or we could have done it the other way round. We could have said, let's imagine we have to wait an exponential amount of time for the first claim and then an exponential amount of time for the second claim, etc. with rate lambda. What is the distribution of the number of claims up to time t? It would be a Poisson. The important result is this. And you can sort of, it helps you remember to me that, of course, if there are lots of claims coming in, so lambda is large, then the waiting time will be quite short. So the mean of the exponential is 1 over lambda. So it sort of reminds me that this relationship between the Poisson and the exponential reminds me that it must be lambda if it's the expected number of claims per unit time, the waiting times must be 1 over lambda, because if we're getting 10 claims per unit time, then we're going to expect only to wait 1/10 of a unit to get the first claim coming in. Another nice result here from the memory list process of the exponential distribution is that if you're looking at the, is this graph getting too messy? I'll change my colour. if you want to look at the distribution of the number of claims between two time points, and again I'm calling them, which way around is it? S here and T, so they're new S's and T's. So we want to look at the rise from here to here, then that is going to be, so that would be N, we've got NS here and NT here, so the jump is going to be NT minus NS. So the number of extra claims that have come in that period, because it's memoryless, we can say, well, we can go back and say it's the same distribution if we started the clock at 0 and just went for the gap between the claims. So that's what this is saying. So the jump between here and here has the same distribution, this is length t minus s, as just starting at 0 and going to some point t minus s. Okay. Which means then we can work out what's the expected number of claims between weeks 10 and 11 will be the same as between 1 and 2, or between 10 and 15 will be the same as between 0 and 5. So a very simple little example here just to enforce it, the results. I mean, sometimes I debate whether to take this example out each year, but then I just leave it in, so let's go through it quickly. So, the claims follow portfolio, they arrive with 2 claims per week. So that's what we've got. We've got 2 claims coming in per week. What's the probability in the first 3 weeks that there'll be no claims? Or 2 claims? Well, the first thing is, what is the Poisson? So both of these will be Poisson distributed. What is the parameter? Well, we're looking at a 3-week period, so we expect 6 claims. Lambda times, so 3 weeks, t is 3, times 2 is 6. So we want to work out what's the probability that n equals 3 or 2. Maybe that's why I think get rid of that, because that's rather a lot of words. Anyway, those are the restatements of the probabilities. The probability that the number of claims in the 3-week period is 0, or the probability that the number of claims in a 3-week period is 2. With the parameters 2 and 3, we know that the number of claims in a 3-week period is going to be a Poisson with rate 6. We know, or we can look up quickly in our tables, the mass function for a Poisson distribution and work out the probability for no claims will be e to the minus 6, of course, and 2 claims will be e to the minus 6 times 6 to the 2 over 2 factorial. That's on the tables, so we can get these probabilities. So that's using the first result. What happens now if we wanted to look at the number of claims, or what's the probability of 4 claims between weeks 3 and 6? Well, now you know it's memoryless, you can say, well, that's still a period of 3 weeks. So that will have the same distribution as the probability of claims between no and 3 weeks. So the probability, so the actual statement is what's the number of, the jump in claims between 3 weeks and 6 weeks is 4. We know from the memoryless process that this will be the same as the number of claims in a 3-week period, any 3-week period. So that will be a Poisson with rate 6, because we know that there are 2 claims per week, and we get another mass. So that's the probability that we wanted, is the probability of 4 claims in a 3-week period. Which again is that. Also, I suppose, that went through my mind, now we can also ask, how long would we have to wait for the first claim here? Well, that would be half a week, because we're expecting 2 a week, so our expected waiting time for the first claim would be half a week, 1 over lambda. Okay, so that may be a very, very brief introduction without any proofs of a Poisson process, and the key results for it is that you use a Poisson distribution to work out probabilities at given time points. Now, this thing here, so I wrote down here, the aggregate claims process. So I defined that without telling you. If you look back a few minutes ago, all I said was that claims were coming in following a process NT, and the claim sizes had a loss distribution. Now, in order to do any mathematics or probability theory with ST, we're going to make some assumptions about this. So we say this aggregate claims process, which is a picture, looks like this, with jumps at every time there's a claim for a random amount, a compound Poisson process if, and these assumptions are going to be very similar to the compound Poisson distribution, but now bearing in mind that we're following this process in time. So the xi's are going to be independently identically distributed with some common loss distribution for insurance, say F. Remember, the CDF is usually what we use to define a random variable. The assumption is that it's only on the positive line. So if there is a claim, it must be a positive amount. It's a standard assumption. So, and you can't have negative claims. So there's no mass below 0 or less than or equal to 0. No 0 or, I could put there, negative claims, but I don't think we'd expect negative claims. But we might anticipate that if a claim comes in and in the end you don't pay out any money, that doesn't count as a claim. This is the assumption that the claim sizes are independent of the number of claims, but now they've got to be independent of the number of claims for any t over time. Which is, so for any particular point nt, it's got to be independent of the whole process of claims coming in. We're going to make the assumption that the claims process is Poisson, which is the line below next. But in some senses, so it doesn't really matter because we're going to have the same process over time. So if it's independent at one particular time, it will be independent at all times. And the final thing to make it a compound Poisson process is that the NT, so this is the NT must switch from a compound, from a Poisson distribution for a distribution to a process for a Poisson process, for a compound Poisson process. And that again, I've written that already a couple of times, but that's just the mass function of a Poisson distribution. So a compound Poisson distribution is a distribution where claims come in independently identically distributed over time. The number of claims coming in follows this Poisson process, and we've got independence between the number of claims and the size of the claims. Okay. But this process is just adding up how much total claims we've got. And we want to look at something called ruin. So we're going to come up with a third process here, which is going to keep track of how much money we have in our account related to that portfolio. So what we're interested in ruin theory, is the probability that at some point in the future, the number of claims, the total amount paid out on the claims, exceeds the premium income. And a little more, because we're going to allow ourselves to start with an initial surplus. So we're going to start with an initial surplus. So I haven't got room to draw this below, but I could draw it below and line up things, but I'll have to just do it approximately. So we're going to start with an initial surplus in the bank at time 0. We're then going to assume that money comes in. People are paying premiums for this insurance. And we're going to keep things simple. We could have premiums coming in at random, which would really muck things up. But usually we can assume that the amount of the money coming in is a linear function of time. So if we don't have a claim, we're going to assume that as time evolves, money comes into our portfolio like this. So for every unit of time, we're assuming that C amounts of money come in. So if I've gone up 1 unit of time, so this thing will have slope C. And so if I never got any claims, this would just go on and on and on, up, until the end of the period I was interested in. So take any point in the future, say 10 weeks in the future, and we're getting £100,000 per week, so 10 weeks in the time we would have £1 million coming in. Then on top of this, we now have to put in the losses. So we now have an aggregate claims process here, which is telling us how we're paying out. So there's an ST here that looks exactly like this. And so I'm now defining what I call UT, which is the surplus process. Slightly confusing, but U is the surplus process, S is the aggregate claims process, to have this form. So this is the reserve at any time t. So what have I got? I've got the U there, I've got the money coming in, and then at any particular point in time, that should, so X1 will be taken off here. Then money will come in, and then X2 will be taken off. Money will come in, and then X3 will be taken off. So that's what the surplus process looks like, that we're going to restrict ourselves to that sort of surplus process. And so it is the amount, so it's a process that at any point in time you can look here and say, this is how much money we have in reserve. So at the start we had U in reserve. Up until the first claim, money came in, we lost a bit, money came in, we lost a bit, money came in. So are we now on to ruin probabilities? Oh yes, we are. Okay, so we're building up to what is the definition of a ruin probability. So this process could happily, well hopefully it continues being positive for as long as we want it to, and we always have positive reserve. But what we're interested in is what's the probability that maybe we wait a very short time and a big gain comes in. So we mean by ruin, and I'll define this more formally, and I'm going to define it in 4 ways. So at the end of today's lecture, yes, we've got time good, so I get all 4 definitions in. You can at least, hopefully you can remember those 4 definitions and the similarities and differences. But they're all related to the probability that this process drops below 0. So they group these ruin probabilities into 2 lots of 2. So let's think of the first 2, the 2 types. So splitting them one way, there is the probability of ultimate ruin, or the probability of ruin in infinite time. So this is just asking ourselves, if we follow this process forever, what's the probability that sometime in the future, forever, it will drop below 0, given your initial surplus? And the notation is, to my mind, forgets lots of things, and so we'll discuss that either a little later or probably on Monday. This thing here, phi of u, is the probability of ruin with surplus u. But you've got to remember that it's going to depend on all sorts of things, like the distribution of the x's and the lambdas, and, well, in fact, the distribution of the x's and the size of the claims. But the notation tends to forget all that and says that all we're now asking about, the other things are given. This loss distribution, the number of claims is given. The only thing we can perhaps control here is the amount of money we start with. The other things are external because they come from just the way the portfolio behaves. So the definition here is phi u, the probability of ruin in ultimate ruin, or the probability of ruin in infinite time, is that this process here drops below 0 for some point t from now, immediately after we start, until infinity. And this, as I said at the beginning, is a little easier to calculate and put bounds on. But it's probably not what we're interested in, because we're going to run this portfolio for, if it's life insurance, 25 years, or if it's car insurance, maybe only a year. So we then have the probability of ruin within a time. So this is called sometimes within finite time. So what's the probability of ruin before a point t in the future? So we have a little bit of notational confusion, but this is usually the way they define them. So this is the probability. So we start with an amount u, but we're going to stop following this process, and this is why maybe I should just change this to be called torque. We're going to stop following the process at a particular point in time t, which may be 1 year, 2 years, 6 months, 25 years. So we only want to ask, what's the probability that you drop below this line so that you're ruined before the point t in the future defined. And so clearly this will be a function of the amount of money you start with and how long you want to wait for. And the part of the syllabus here, which is what you need to know, is learn these definitions and the relationships between these things. And it gives you an understanding. So we get some inequalities here. And they're useful because if we can bound something, then we can bound something else. So these are pretty obvious, but okay. This is if you start with more money, U2, then you're less likely to be ruined. So U2 here is larger, start with more money. Obviously, at the same point in time, if I start with more money and I stop after the same point of time, I'm more likely, lower probability of being ruined. Okay? And of course, again, in infinite time. So if I start with less money and go on forever, or start with less money and go on forever, then I'm more likely to be ruined. I mean, that's pretty obvious. So if we shift this process up, it's going to fall below zero slightly less. If we shift it down, it'll fall slightly more. The other thing is, again, the longer we wait, the more likely we are to be ruined. So the important thing here is it's a drop below some time up to now. It's not if we're below at this particular point in time. So you could imagine that this would go back up. And in a moment I'll say a little more about this. But the important thing here is that if you drop below zero here, you have been ruined. So when you're asking, am I ruined at time 1 year, you can see the maths gets quite difficult. I can't just look at 1 year and do the maths. I've got to go, was I ruined after 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 10 seconds, 2 days, 5 days, 10 days, to a year. So if you drop below it, I mean, if you're very unlucky, you get the claim within a second or two of starting, you could be ruined. But this is saying the longer you wait, the more likely you are to be ruined. Because the event of ruin happening before here is included in this event, and there's greater chance of ruin. And also a pretty obvious thing that if you let t tend to infinity, so find ruin in finite time, and then let t tend to infinity, you get the ruin in infinite time. In fact, it of course attends, the previous result says it's going to come from below. This is going to tend to this limit from below. So this thing here will never go greater than, which is sort of what we're saying here. For all t here, this will never go greater than. So I've introduced two types of ruin. One is in infinite time, one is in finite time. But what we've been doing is we've been measuring time continuously. So as I said, we've been checking every minute of every day. Now, the other two types of ruin, you don't check every second of every day. So you might say, if you're checking every second of every day, this is continuous time. So we're now going to do discrete time. So those would be called continuous time ruin probabilities. So there's a little table in your head, hopefully. Infinite time or ultimate ruin and finite time, continuous time, discrete time, with the 4 definitions. So let's just say why it might be. Sometimes it's more realistic. It's often easier computationally to consider discrete time Ruin probabilities. So we only check for Ruin, say, at the end of the day, or the end of the week. So in this case, let's say, I've exaggerated this, this is the end of the week. So this is 1 week in. Then I'm not bothered if during the week, or maybe the better for the day, if I drop below 0. But what at the end of the week, I want to be positive if I'm not ruined. So all we're going to do is check at discrete points in time, say every day, at the end of each day, or the end of each week. And we're not going to be bothered what's gone on between the times we check. So in this example, the next check would be here. So all I'd be interested about is, am I positive at this check point? And then the same length again. Sorry, it's getting, but you get the idea. I want to look here. So the definition now is very similar. It changes slightly. So this is the probability of still ultimate ruin. So will I ever be ruined? But I'm only going to check at time increments h. So there's this little extra here, which is a measure of time of how often I'm going to check. So it's now, am I ruined? The probability that the surplus process, this thing has dropped below 0 at time points, say, 1 week, 2 weeks, or 1 day, 2 days, 3 days, 4 days, 5 days, 6 days, 10 days, ... forever. So that's the third one. Discrete time, discrete and ultimate time. The final one is discrete and finite time. So now, the same idea, we're only going to check at the time h, 1 day, 2 day, 1 week, 2 day, weeks, 3 day, weeks. And we're only going to check up to t in the future. So we are ruined if the ruin probability is the probability that the surplus process is below 0 for some tau in the points h, 2h, ... Now, different books will do the final t. I'm just making this t to be a multiple of h. If it's not, it's clearly the final check will be the greatest multiple of h less than t. So you can see it gets a bit complicated, but sometimes people would replace that final t as the greatest multiple of h less than t, because that's the last time you're going to check. So if you're checking every week, and you want to know what's the probability of ruin in the first month, then you would look at 28 days. You'd look after 4 weeks, even though you were asking for, say, 30 or 31 days. But I've made it simple. Okay. And we get some similar results here. And again, they're not difficult. In fact, the first 4 results there are identical. I think all I've done is write a little h on the previous slide. So we can go quickly through them. But if you took my previous slide, I've just written a little h on everything there. So if you start with less money, you're more likely to be ruined. In finite time, if you check at the same time point, and in infinite time, start with less money, more likely to be ruined. We're just checking at every age. Here, if you wait longer, you're more likely to be ruined. And of course, if you're going to consider the infinite process, then that's even more likely to be ruined. And again, if you let t tend to infinity, in fact this will tend to this from below, so as you go further and further, this becomes close to this. And as I said, these things are often easier to calculate. So if t is a reasonably large number, you're at least going to get an upper bound on the probability of ruin in 25 years by looking at the probability of ruin in infinite time. And you will see from some graphs at the end of the shape of these things suggests that they flatten out. So after a certain amount of time, the probability of ruin doesn't really increase. The final statement, which is a relationship, or two statements, is the relationship between discrete time and continuous time. So hopefully you can see this first one if I move that away. That says the probability of ruin with initial surplus u up to a point time t is going to be less if we check less often. Okay, you can sort of see that. This one doesn't allow for the fact that you can ever go below 0. So this side here says I've got to check every second of every day. So this would be a ruin under the first definition, whereas under this definition it wouldn't count as a ruin. So hopefully you can see that the probability of ruin checking every day is going to be less than the probability of ruin checking every minute or every second or infinite time. So again, if I'm really interested in checking every day, but I can work out this thing easier, mathematically I can get this, then I would at least have an upper bound, and that's what we're really interested in. We want to control our probability of ruin. We'll see some examples next week about how we decide how much u we should keep to control the probability of ruin. So we may be being rather cautious, but at least if we can say we know the probability of ruin will not be less than this, then we're okay. And so the final two things is that, of course, logically, as age gets smaller and smaller and smaller, the probability of ruin in discrete time will tend to the probability of ruin in continuous time. So again, you expect that to be obvious. And the same. Okay, so this lecture was really about definitions. So you really just need to go and pull out the things you need to learn. So a Poisson process, a compound Poisson process, a surplus process, a aggregate claims process, then a surplus process, and 4 definitions of probability of ruin. 4 need to be learned, and the relationships between them. So it's just a definitional lecture, but we'll do something a bit more about how we calculate them, probably a little on Monday and then on Tuesday.